Hey, Twiggy here. Welcome back. This is our last week. Uh, Glad to be back. Mr. Krolak's nephew, if you don't remember. And we're going to be talking about events and probability today, which is something you've probably seen in the past. So let's get cracking. Alrighty. When we talk about a random experiment, that just means it's something that we don't know how it's going to end up. Okay, we don't know what the result is at the end. We do know what the possible results are. All right, so those possible results are called the sample space. So we take a simple example like flipping a coin once. Our sample space is either a heads or a tails. If we flip a coin twice, our sample space is either a heads and a heads or a heads and a tails, etc. Okay, flipping a coin 3 times. Here's our tree diagram for that sample space. If we wanted to get the sample space for flipping 4 coins, then we just continue on with our tree diagram and add a heads and a tails to each one of these nodes where it ends there. Okay, so the first thing said a coin is flipped 4 times. Okay, what's the sample space S for this experiment? So all I did was, since I had this already uh, drawn up here, was I took each outcome. So the first outcomes was heads, heads, heads. And then I wrote it twice because I could have a heads, 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 or I could have 3 heads and a tail. So if you look right over here, I took the 8 outcomes that were possible for 3 coins, and then I just wrote each one of those outcomes twice. So I could have a head here followed by a tail. So my next possible outcomes would be 2 heads and a tail. So I wrote that twice, 2 heads and a tail, and then if I had a fourth coin, a head and a tail. And I did that for each one of these then. Okay, so let's just say we worked our way down to this one. Tails, heads, heads. Okay, so tails, heads, heads. And I could either have I wrote it twice because it could be 2 more out. So I just did that for each one of these. And then now, instead of having 8 outcomes, we've got a total of 16 outcomes. So this would be known as the sample space for flipping 4 coins. Okay. All right, now the second experiment said, well, what if you just looked at what's the sample space if you only counted the number of heads? All right, so if we went back to these and we just counted the number of heads, what possible values are we getting? All right, so on this first one, I get 4 heads, so 4 is in that sample space. 3 heads, 3, 2, 3, 2, and I'm just going down here and I'm counting the number of heads. And then any number in this list would make up my sample space if I was just considering heads. So I could get 0 head, 1 head, 2 heads, 3 heads, 4 heads. All right, theoretical versus experimental probability. Okay, experimental probability just means you're doing trials, and then you're taking the number of trials of what you were looking for over the number of trials that you did. So here's an example of experimental probability. All right, if I took one of those cones, like a cone shape that you get, like a what should I call it? Uh, Snow cone. Yeah, snow cone. All right, and you flipped it 279 times. out of that 279 times, it landed on its side 183. So figuring out this relative frequency right here would be the same as getting your experimental probability. Okay, so for landing on its side, it would be about 65.6%, and landing on its base was 96 out of that 279, so 34.4%. That's theoretical probability. Okay, experimental probability is if I know something is equally likely to occur, like a fair coin, or in this case, a spinner that's divided into 8 equal parts, I could calculate what the probability is theoretically just by, okay, I said, what's the probability of getting a 2, of spinning a 2? There's 8 outcomes. One of them is a 2, so that's the probability. And the probability of getting any one of these would be the same. They would all be 1/8. Okay, we don't have to do an experiment. We can say we know that this is what the probability would be. Now, if we did do an experiment, let's say I did this 100 times, then I should see that 1/8 out of those 100 times should be a 2. And the more times I spin this, the closer the theoretical, or the closer the experimental probability would be to the theoretical. And you have an example of that in your cognitive notebook. When you click on this GeoGebra applet here, okay, it's modeling the proportion, okay, of times that you have heads. Okay, so out of 20 flips, okay, so that's 20 flips. Okay, so right now the proportion's over a half. Okay, as I go to 50, okay, didn't change a whole lot. As I go to 100, you can now see I did it 100 times. Now that probability starts to level off at whatever the theoretical probability is. That's assuming that this is a fair coin. All right, so our notation for probability is whatever the event is that we're looking for. We call that, in this case, we'll just call it A. Okay. N of A, so this is the probability that some event A will occur. A could be landing on a heads, or A could be spinning an even number, whatever. This is the number of times the event that we're looking for occurred. This is the number of times we did the experiment. Okay? Or if we're talking about theoretical probability, okay, this would be, if I said, what's the theoretical probability of spinning a 2? Well, we know that out of that sample space, there was only 1 2, and there were 8 outcomes, so that's the theoretical probability. If I actually did an experiment, okay, so if I did this 100 times, I would expect, oh, let's make it easy. Let's make it 80 times. Okay, I would expect that if 1 out of 8 is a 2, then I should end up with 10 out of 80 being 2s. If I did that experiment. Okay, probabilities we know range from 0 to 1. Okay, if something isn't very likely to happen, it's going to be closer to 0. If something's very likely to happen, then it's going to be closer to 1. And obviously, if it's equal, then we say it's 50-50. All right, so second example here. It says 4 boys, 6 girls are waiting to see the doctor. Receptionist not remember who arrived first. If the receptionist chooses one of the patients randomly, find the probability that a boy is chosen. Well, altogether, you've got 10. So n is 10. And out of those 10, 4 of them are boys. Okay, so the probability of randomly choosing a boy, very simple, is just 4 out of 10, or 2 out of 5, or 40%. Our next example, a normal 365-day year, find the theoretical probability that someone has a birthday in August. All right. So the number of days in August is 31. Okay, the number of days in a year, 365. So our ratio is simply 31 over 365. And if you divided that out, you would get 0.0849. So about an 8 point, roughly 8.5% chance that a birthday is in August. All right, now what's known as the complement of an event? That simply is the rest of the probabilities. So if the complement of an event is, or let's say the probability of something happening would be 3/8. Okay, then the probability of A not happening, that's what that stands for, that would be, well, whatever's left over. Okay, so 3/8 was probability of it happening, then 5/8 would be the probability of it not happening. All right, you add these up, you're going to get 1. So to find the complement, you simply take 1 minus whatever the probability of the event was, and that gives you the probability of the complement. So, for example, let's find the complement of rolling a 2 with a dice. All right, well, if you look at the sample space for rolling a die, you're going to get a 1, 3, 6. Okay, the probability of rolling a 2 is 1 out of 6. So the probability of not rolling a 2 would be 1 take away 1 out of 6, which is 5 out of 6. All right, another example here of showing how using a complement, uh, thinking of things in terms of their complements. So if the example was, what's the probability of not having your birthday in August? So I write not August. Well, we know that there's 31 days in August. So then out of the whole year, there would be 365 minus 31 days. That would not be in August. And that would give us our probability. Okay, a quicker way of even thinking about it is you already know the probability of August. So the probability of not August would be 1 take away the probability of August, which was right here. So P August, and then that would simply be 1 take away 0.049, and that would give us the same probability as dividing out this fraction, which would have been 0.915, or about a 91.5% chance of being born some other time. So that's using the complement to calculate a particular probability. All right, here's another example of how thinking about complements can make your work a little less tedious. So there's an example described here in this paragraph saying that if you know the probability of serving an ace on one serve and your team serves the ball 25 times a game, all right, and you needed to find out, well, what's the probability of getting at least 2 aces out of those 25? Well, what you'd have to do is you'd have to find the probability of getting 2 aces. Then you'd have to find the probability of getting 3 aces. An ace, if you don't know, is when you serve it and they don't serve it. They can't return the serve and you get a point. So you'd have to do this all the way up to, because each one of these is at least 2. That's 2 or more. So I'd have to keep going, going, and going. Well, if we think about it in terms of its complement, all right, well, the complement would be this. Finding out all of those would be the same as taking 1, subtracting, well, the probability of less than 2 would be, figure out what the probability of getting 0 aces would be, the probability of getting 1 ace, okay, and if we subtract those from 1, we're going to get the same as the probability of at least 2 aces. So here's another instance of thinking of things in terms of their complement, as opposed to finding the probabilities directly. All right, so that's what this is talking to you about in this box that's highlighted here in pink. Finding the probability of at least A, so whatever A stands for, that's your event, at least one of them occurring would be the same as taking 1 minus the probability that A did not occur. That's the complement. And then that would be the probability that you're looking for. All right, there are times when we're doing theoretical probability questions. All right, there are times when we're doing theoretical probability questions that will end up using combinations to figure out how many total items that we have. Okay, so our example is, if we had 24 teachers in our school and we had 75 students, and we're going to figure out how many combinations are there, how many different ways can we choose 3 out of 24 teachers. So that would be 24 choose 3. And how many different ways could we choose 12 out of 75 students? So that would be 75 choose 12. Now, what we're doing is we're taking the number of committees. How many different ways could we form a committee to plan a school event? And that committee is made up of 3 teachers and 12 students. How many different possible committees could there be? Well, we could figure out how many possible combinations of teachers we could have, and then each one of those combinations could be paired with one of the combinations of 12 out of 75 students. So we're talking some pretty big numbers here. All right. So if I substitute this into my combination formula, all right? And now do the arithmetic. So remember, 24 factorial is 24 times 23 times 22 times 21 times 20, etc. So what would happen is everything beneath 22 or lower than 22 would get canceled out by this 21 factorial. So that's all I'd be left with in the numerator. And then I have 3 factorial, which is 3 times 2 times 1. And then I can do some canceling with that. For example, 3 goes into 24 8 times. 2 goes into 22 11 times. And I'm left with 8 times 23 times 11. And that would be the number of different ways I could group 3 out of 24 teachers. Okay, so for the 12 out of 75, we're not going to work this out by hand, because that would be ridiculous. So you can do these on Desmos. So if I wanted to do 75 choose 12, the way you type it in, if you go down to your calculator here and hit functions, and under stats, you'll see NCR. Okay, that's how we type in what we want. So we click that, and I just put in 75. And R is how many I'm choosing. So I go comma 12. And then that gives me how many possibilities there are. So you can see that's a really big number, 2.6 times 10 to the 13. That's crazy. So this number of combination of teacher, 3 group of teachers, would be paired. Each one of these combinations would be paired with one of these. So to find the total number of combinations, we would have to take the 24 choose 3 and multiply it by the 75 choose 13, which means we're multiplying this number, or 12 I meant, and this number, which becomes huge. All right, so let's just use Desmos to do that for us. Okay, so I'm going to go the combination of those two and then just multiply. So I'm going to type in, let's see, CNR. So I've got, my first one was 24 choose 3. And now I want to multiply that by and this is going to be 75 choose 12, and then that would be the total number of combinations in that school. How many different ways you could pick a committee that had 3 teachers out of 24 and 12 students out of 75. All right, here's another example using combinations where we don't get into extremely large numbers. So you got a deck of 52 cards. Suppose you select 5 cards. What's the probability that exactly 2 of the 5 cards are face cards? That's your jack, your queen, and your king. All right, so to find that probability, let's do it over here. We're going to say exactly 2 out of 5 are face cards. All right, so we can set this up real similar to how we set up the last one in terms of getting the total number of combinations. So there's 12 face cards in a deck. 4 of each, 4 jacks, 4 kings, 4 queens. So first thing we're going to do is how many combinations are there of 2 out of those 12 face cards? So 12 choose 2. Then for every one of those combinations, that can be paired up with one of these combinations, which is, well, there's 40 cards left. This would be choosing 3. How many different ways could we choose 3 out of those 40? That these would be your non-face cards. So I'm going to find that product, and then I'm going to divide it by, this is the total number of 5-card combinations I could get out of a 52 card deck. So we'll use Desmos to go ahead and do these calculations. All right, so to type this in, I'm going to go parentheses. I'm going to do the top of this first. Okay, so parentheses, function, combination, and we're doing 12, choose 2. That's how many different ways I can pick 12 cards. Okay, times the number of combinations of picking 3 non-face cards out of the remaining 40. So that's 40, choose 3. Okay, and then so that's going to be my numerator, and then I'm going to divide that by the number of combinations of 52, choose 5. And then if I rounded that to the if I went out to 3 sig figs, it'd be 0.251. So taking that out to 3 places, 0.251. Bring that back over. So around 25.1% chance. All right, section questions. Which of the following represents the event that is least probable? Okay, well, probabilities are always going to be positive. The closer they are to 1, the more probable that they are. The closer to the 0, the less probable they are. So number 1. Number 2, in rolling a fair die and adding up the numbers. So let's say you got 2 dies. This is the results of 1 die. This is the result of the second dice. And then in the boxes are the sum. So 1 plus 1, 2, 1 plus 2, 3, etc. All right, what's the probability of a number being a multiple of 4? So this is already set up. And the times that you get a 4 are highlighted here in yellow, multiples of 4. So there's 3 multiples of 4, then there's 5, and then there's 1 more. So altogether, there is 9 opportunities where you get a multiple of 4. Out of all of the possible outcomes here, there's 36 different outcomes. So then the probability of getting a multiple of 4 is around 25%. When a coin is tossed 4 times, recording whether it is heads or tails after each toss, what's the probability of having at least 3 tails? So at least 3 tails would be made up of the probability of 3 tails plus the probability of 4 tails. So over here is our sample space that we did earlier. And we just count the number of times where we've got 3 or more. So there's 2, 3, 4, 5. So there's 5 times where we have more than, out of the 16, that we've got more than 3 or more. 4 of them out of the 16 are 3. and there's one of them out of 16 that is 4. So altogether, 5 out of 16 is our probability. Okay, a goalkeeper has saved 78% of the shots on her goal this season. Find the experimental probability that she will not be able to save a shot on goal. Give your answer as a percentage. Well, that would be the complement. So if the probability of a save is 78, then the complement of that would be not a save, which would be 1 take away the probability of a save. So it's just 100 minus 78. So that would be 22%. A box contains 3 balls, 1 red, 1 green, 1 blue. 1, 2, 1, 2, 1, 2, 1. Alright, I've got a box that contains 3 balls, 1 red, 1 blue, 1 green, 1 blue. Draw a ball out, note its color without putting it back, then select the second ball out of the box and note its color. Find the probability that you did not select a green ball. Give your answer as a fraction in lowest terms using a slash. Oh, so this is how when you're typing it in. Okay, so a couple of ways you can do this. One is, if you just think about the situation this way, you got a red, we got a green, we got a blue. All right, so my first pick, I'm gonna pick one of these. So the probability of not green is 2 out of 3. All right, so once I pick that first one not being green, then there's only 2 balls left. Okay. So if I pick the red one, then I'm going to be left with a green and a blue. Or if I pick the red one, I'm going to be left with a green and a red. That means if I pick the blue one. Okay? So if I pick the red one, then I'm left with a green and a blue. If I pick the blue one, then I'm left with a green and a red. So the probability out of the possibilities on the left, the probability of not agreeing in either one of those is 1 out of 2. Which gives me 2 out of 6, which is 1/3. Or what I did was I made a tree diagram, and I just went through all the different possibilities here, and I can see that there's 2 out of the 6 that don't have green in them, so that's 1/3. Okay? Another way is multiplying, when you're using a tree diagram, by the way. If you're finding the probabilities along a branch, you multiply. And then if you're finding the probabilities of more than one branch, you add those results. So this is what I mean. Okay, probability of getting a red is 1/3. And then the probability, I don't want the next probability right here is a half. So let's see, excuse me. Okay, the probability then is 1/3 times 1/2, which is 1/6. Okay, that's doing the red, the blue. That would be 1/3 times 1/2, which equals 1/6. Oops. Now the other one that has would be that doesn't have green in it would be picking this blue and then picking a red. So that would be 1/3 again times 1/2, and that is 1/6. So when I'm moving this way along my chart, I multiply the probabilities at the different along the different branches. Then add those two, I get 2/6, which reduces to 1. Okay, that's it. We got one more lesson tomorrow, and then it's all she wrote, and we're done for the year. Take care, guys. This is Twiggy signing off.